I'm going to introduce another way. Now we're going to talk about what is called the Taylor series expansion. In order to fully understand this, it's necessary to have a foundational understanding of calculus. That's beyond the scope of this lesson, so I'll simply present you with the result and how we can apply it to our current situation. Sine of x can be represented as an infinite series, meaning there are an infinite number of terms in this polynomial. Notice the pattern. It's only odd numbers. X to the first, x to the third, x to the fifth, x to the seventh. Each coefficient is the factorial of the power. So 3 factorial, 5 factorial, 7 factorial matches the power. Remember the factorial, example 5 factorial is equal to 5 times 4 times 3 times 2 times 1. In this case, that's 120. So I can rewrite these. Sine of x is equal to x minus x cubed over 6 plus x to the fifth divided by 120 minus x to the seventh divided by 5040 plus an infinite number of more terms. We'll see here soon that it's not necessary to go beyond a certain number of terms. In order to use the Taylor series, we need to convert to radians. So 58 times pi radians for every 180 degrees is equal to 1.012291 radians. That's important. So now if I were to plug that into this equation above, sine of 1.012291. So I'm getting 0.848045. You remember from before that the exact value is equal to 0.848048. So, keeping 1, 2, 3, 4 terms, we are accurate up to the 5th decimal place. In the 6th is where we have our deviation. Now notice how my input, 1.01, is greater than 1. So each time I raise that to a power, cubed to the 5th to the 7th, notice it's getting bigger and bigger. It turns out if you carry out enough terms, the factorial also gets bigger and bigger to the point that the overall quotient, numerator over denominator, 0.17, 0.0088, 0.0002, this is getting smaller and smaller. But it does make our computation less efficient if we have to carry out more terms. What if we could input a smaller value? Well, that's where we bring it back to the trig identities. So how about using a double angle identity with sine of 29 degrees, 29 being half of 58. Convert 29 degrees into radians. Multiply by pi over 180, and I get 0.506145. Same thing, I'll plug it into my Taylor series expansion for sine. So I'm getting 0.484810. Notice a quick comparison of the terms. Because my angle, because my radian measure 0.506 is smaller than 1 each time I raise it to a power. So cubed to the 5th to the 7th, it's getting smaller and smaller. At the same time, the denominator, factorial, is getting bigger and bigger. So a smaller number divided by a bigger number is an even smaller number. This converges much more rapidly. Compare this. There's 5 zeros in the 4th term. Here there's only 3. So we're gaining 2 places of accuracy just by the 4th term when we truncate it. Hopefully you can see why that is beneficial. To have a smaller angle measure makes the series converge more rapidly, is what we say. In short, fewer computations to obtain the same level of accuracy. Here I have a couple of options. There's a similar series for cosine, or I can use the fact that cosine of 29 degrees is equal to the square root of 1 minus sine squared of 29 degrees. So by plugging that into my calculator, I get 0.874620. Now, using my trig identity that sine of 2 theta is equal to 2 sine theta cosine theta, I get .848049. All right, how does that compare? Not bad. If we had carried out more digits of accuracy, we would have converged on this value. That's not quite how your calculator computes the trig values, but we're getting closer to the heart of the matter. There's not a little table inside here of values that it's looking up. It's running through some sort of algorithm where you can input any value and it will spit out the correct value. Notice how our table has limitations. In that case, every 3 degrees or less on this table. So that's the value of the Taylor series expansion, to get a true numeric representation of the value. So in summary, how do we relate the angle measure of a triangle to the side length? Using our 3 functions, sine, cosine, and tangent. We use geometry, the equilateral triangle, the square, and the pentagon, to obtain some exact values at those specific angles. Then we use trig identities to fill in the gaps on the rest of the table. Of course, the table still has its limitations in that not every value is represented. That's why we introduced linear interpolation to fill in the gaps between the values on the table. Now, linear interpolation also has its limitations. That's why we introduced the Taylor series expansion, where we can convert an angle measure into radians and plug it into this infinite polynomial, truncate it at a certain number of terms, in this case 1, 2, 3, 4 terms, and we obtained accuracy up to 5 decimal places to the true value. So we have geometry to make a table using trig identities, linear interpolation, and the Taylor series expansion. Those are 3 ways. You may have asked yourself, because sine is a curved function, why are we using a line to interpolate between 2 points? Couldn't we use a curve? Why, yes, we can. In fact, one of the preferred methods of interpolation is to use the cubic spline. That is a 3rd order polynomial. We may or may not cover that in a future lesson, but be aware that option does exist.